Let's jump right into today's explainer, covering the newly released June 2026 research paper on DreamX-World 1.0. This is an absolutely massive leap forward for AI video generation. We're looking at a system here that completely goes beyond just making a picture move. It's a general-purpose interactive world model. So today, we're going to break down exactly what that means, how the team built it, and why the results they published have the AI research community paying very, very close attention.
Here's a quick look at our agenda. First, we'll meet DreamX-World 1.0. Second, powering the data engine. Third, fixing the memory problem. And fourth, benchmarks and speed tests.
All right, part 1. Meet DreamX-World 1.0. Let's get right into what the DreamX team actually built to get past the limitations of current short clip AI video generation.
To really grasp the breakthrough here, we need to understand what an interactive world model actually is. The paper defines it as a text or image-to-video AI capable of controllable long-horizon generation, camera navigation, and promptable events. Basically, instead of just spitting out a brief, static video from a text prompt, this model acts like a fully interactive environment. You can literally navigate the camera through the generated space and trigger specific events to happen as you go. It's a total game changer. And what's super cool is the sheer flexibility of this thing. DreamX-World 1.0 isn't locked into just one visual style. We're talking photorealistic videos that look just like real life, game-style environments, and even heavily stylized artistic domains. The architecture is flexible enough to seamlessly adapt to all these different visual demands. Moving right along to part 2, powering the data engine. Let's look under the hood at how they actually taught this model spatial awareness.
Generating a world you can actually navigate requires an enormous amount of geometrically accurate data. The team didn't just scrape random videos off the internet. They built a massive pipeline combining camera-accurate, Unreal Engine renderings, action-packed gameplay recordings, and real-world videos where the camera geometry was actually recovered. By doing this, they fed the AI the exact spatial data it needed to really understand how a camera moves through 3D space.
But of course, having the data is only half the battle, right? To actually execute that camera control, they introduced something called E-PRoPE. Now, the paper defines this as a lightweight variant of projective positional encoding, applying camera-aware attention to spatially reduced tokens. Which, yeah, I know, sounds incredibly complex, but in plain English, it essentially gives the AI a highly precise mathematical map of exactly where the camera is and what it should be looking at.
With that geometric understanding locked down, the team then converted a bidirectional video generator into a super-fast autoregressive world model. And they did this using 3 very specific algorithmic steps: causal forcing, DMD-style distillation, and long-rollout training. These steps streamline the model, letting it generate the environment sequentially and highly efficiently. Okay, part 3, fixing the memory problem. This is a huge one for sequential AI video generation. We've all seen those AI videos where a red car slowly turns purple or a door just vanishes when the camera pans back, right? That's because standard training accumulates style and color drift over time. The system literally forgets the original visual parameters. But DreamX-World 1.0 fixes this by relying on that long rollout training we just mentioned. By constantly exposing the model to its own generated history, they basically entirely stop the color and style drift that ruins so many AI videos. And they went even further. They implemented a feature called memory-conditioned scene persistence. Basically, if the camera pans away from a room and then turns back, the AI can actually retrieve those earlier views based on the camera geometry. It remembers what was there. Plus, they use something called residual recycling, which makes the whole system much less sensitive to imperfect memory latents. To really dial in the final behavior, they used a couple more tuning techniques. First, event instruction tuning, which gives you that precise, composable control over events in the environment. And second, they hit it with reinforcement learning alignment. This guarantees great visual fidelity and recovers the camera control after the distillation process. Finally, part 4, benchmarks and speed tests. We've talked theory. Let's see how fast and accurate this model really is against the competition. Speed is usually a massive bottleneck for AI video, but DreamX-World 1.0 hits an incredible 16 frames per second. To pull this off, the team optimized everything. They used mixed precision DIT execution, residual reuse, and they actually pruned 75% of the VAE decoding process. Combine that with asynchronous pipeline parallelism running on 8 RTX 5090 GPUs, and you get a seriously fast system. And the crazy part? They didn't sacrifice quality for that speed. On their 5-second evaluation, DreamX-World 1.0 scored an overall 84.76. It indisputably dominates the current competition, cleanly beating out HY-WorldPlay 1.5 at 80.79 and LingBot-World at 80.45. Beyond the overall score, there's one specific metric I want to highlight. They hit a 73.75 camera control score. This number is absolutely crucial because it proves that their unique E-PRoPE system, that complex projective positional encoding we broke down earlier, actually works beautifully in practice, giving you precise navigation within the generated world.
So, wrapping up this explainer, we've seen how incredible data pipelines, innovative math like E-PRoPE, and long-rollout training have all come together to create a genuinely navigable, persistent AI environment. And I'll leave you with this exciting question to ponder. As these interactive world models become even faster and more realistic in the coming years, how will they ultimately reshape our digital reality? Thanks so much for diving into this with me today.